In this section, we're going to look at inverse functions. When you think of inverse, I want you to think of trading places or switching the domain and the range, which are just the x and the y's. Let's look at the relation of ordered pairs. 1 goes with 2, 3 goes with 4, and 5 goes with 6. In order to find the inverse of this relation, all you have to do is trade the x's and the y's. Instead of 1, 2, we're going to have 2, 1. Instead of 3, 4, we're going to put 4, 3. Instead of 5, 6, we're going to put 6, 5. Now, if we looked at a mapping of the original relation, 1 goes with 2, 3 goes with 4, and 5 goes with 6. Notice that this is a function because each domain is paired with exactly one range. In order for a function to have an inverse, it must first be one-to-one. If we look at that definition, a one-to-one function is a function where each range is paired with exactly one domain. So let's go back to our original mapping and take it backwards. Is each range paired with exactly one domain? If we take it backwards, 2 goes with 1, 4 goes with 3, and 5 goes with 6. So not only do we have a function here, we have a one-to-one function. Matter of fact, if we look at the function, our domain is going to be 1, 3, and 5, and our range is going to be 2, 4, and 6. If we look at the inverse, the domain is going to be 2, 4, and 6, and our range is going to be 1, 3, and 5. So notice not only did we switch the x and y on the points, the range of the function became the domain of the inverse, and the domain of the function became the range of the inverse. So we did switch domains and ranges. Now, for a one-to-one function, there are two ways to tell if you have a one-to-one function. One is called the algebraic test, and the algebraic test states that if the function using an a is equal to the function using a b, you need to prove that a equals b. Or we can do something called the horizontal line test. You'll remember the vertical line test. If we have a function and we draw vertical lines on there, as long as each vertical line only touches one point on the function, you definitely have a function. A one-to-one function is the same thing, except your lines are going to go horizontal. At least for every horizontal line, if the horizontal line only touches one point on the function, then you have a one-to-one function. Let's look at some specific examples of this. Let's start off with the function f of x equals 3x plus 2. Algebraically, to test if this is one-to-one, we're going to set the function using an a equal to the function using a b. So 3a plus 2 is equal to 3b plus 2. If I subtract 2 from both sides, I'll be left with just 3a equals 3b. Now, if I divide both sides by 3, I'll be left with a equals b. Since I proved a equals b, I know I have a one-to-one function. Looking at a different function, let's look at the function g of x is equal to x squared minus 2. To algebraically prove if it's one-to-one, we set the function using an a equal to the function using a b, and try to solve a equals b. Add 2 to both sides to get a squared equals b squared. There we can just take the square root of both sides, remembering to put the plus or minus, so plus or minus a is equal to plus or minus b. Here I did not prove a equals b because positive a could equal negative b, and positive b could equal negative a. So this function is not going to be one-to-one. We can pull that up on a graphing calculator and look at the vertical line test for that. If we plug in the original function of f of x as 3x plus 2 and look at that graph, notice that the graph passes not only the vertical line test for being a function, but it will also pass the horizontal line test to be a one-to-one function. Now, if we look at the function of x squared minus 2, you will notice that it's going to fail the horizontal line test anywhere above y equals -2. Because if we draw a horizontal line, we will touch more than one point actually on the graph. To find an inverse of a function, and we're going to do three things. We're going to switch the x and y. We're going to solve for y. And we are going to replace the y with inverse notation. So let's talk about the inverse notation. Instead of actually writing out the inverse of the function f of x, if f of x is our normal function, we can just write the notation f-1 of x, which just means the inverse of f of x. Just a quicker way of writing that out instead of having to actually write the words. So let's look at an f of x function actually equaling 2x plus 5. To see if it's 1-to-1, we're going to go to our graphing calculator, type in 2x plus 5. Notice here that we not only have a function, but we have a 1-to-1 function, so we can actually try to find the inverse. Remember, f of x and y are interchangeable. Then to find the inverse, we trade places with the x and the y. So x is going to equal 2y plus 5. And then we're going to solve for y. Subtract 5 from both sides. So x minus 5 will equal 2y. Divide both sides by 2. And x minus 5, all divided by 2, is going to equal y. So our inverse is going to be x minus 5 over 2. Notice the domain of the original function, since there's no fractions or even indexed radicals, is going to be all real numbers. The domain of the inverse is also going to be all real numbers, even though we have a fraction, because the bottom of this fraction can never equal 0. Once you figure out the domains, you can just easily find the ranges by switching. Since the domain of the function is all real numbers, the range of the inverse must also be all real numbers. Since the domain of the inverse is all real numbers, the range of the function is going to be all real numbers. Let's step up and look at a rational function. Let's take the function g of x is equal to 3 divided by x minus 2. Note right here that we can say the domain of this function is x is not going to be allowed to equal 2. So before we even find the inverse, before we even know what that function is, we already know that the range is going to be y cannot equal 2, because the domain of the function is going to be switched to the range of the inverse. Now, to find the inverse, we're going to switch places with the x and the y. So we'll have x will equal 3 over y minus 2. I now want to clear the fractions, multiply both sides by the denominator of y minus 2. On the right-hand side, that's just going to cancel my fraction out and leave me with 3. On my left-hand side, I'm going to distribute to get xy minus 2x. To solve for y, I'm going to have to add 2x to both sides, leaving me with xy equals 3 plus 2x. Divide both sides by x, and we'll have the y by itself of 3 plus 2x, all divided by x. So our inverse is going to be 3 plus 2x, all divided by x. If we look at that domain, bottom of the fraction cannot equal 0, so we know that x is not going to be allowed to equal 0. That's going to be the same thing for our range of the original function, or y cannot equal 0. Let's do a very quick review on these rational functions. Remember, they have undefined portions of the graph, or asymptotes. Domain and vertical asymptotes go hand in hand. If our domain is x cannot equal 2, our vertical asymptote is at x equal 2. On our inverse, our domain is x cannot equal 0, so we will have a vertical asymptote at x equals 0. For the horizontal asymptotes, we look at the degree of the numerator, compare it to the degree of the denominator. If the numerator is less than the denominator, your horizontal asymptote is always going to be at y equals 0. Or if the degree of your numerator matches the degree of your denominator, your horizontal asymptote is going to be y equals lead coefficient of the top over lead coefficient of the bottom, which is just y equals 2. Just like domain and vertical asymptotes go hand in hand, range and horizontal asymptotes also go hand in hand. Let's look at one more rational function before we end on this note. Let's look at h of x is equal to 3 minus x over x plus 2. Our domain is going to be x is not allowed to equal negative 2. So again, before we even find that inverse function, we know that the range of the inverse function is going to be y cannot equal negative 2. We want to first look and see if we have a one-to-one function. So we're going to go to our y equals. We're going to type in the top 3 minus x, all divided by the x plus 2. Notice that I'm putting both the numerator and the denominator into parentheses because they're more than one term. And when I graph rational functions, I really should be graphing in the dot mode. So I'm going over to the left of my y equals, changing that to dot, and looking at the graph. It not only is a function, it's a one-to-one function, so we can find that inverse. To find the inverse, we're going to trade place with the x and y, and we're going to solve for y. Clearing the fraction, multiplying both sides by y plus 2 is going to leave me with xy plus 2x is equal to 3 minus y. Getting the y's to the same side, I'm going to add y to both sides. Xy plus y plus the 2x will equal 3. Subtract 2x from both sides, so xy plus y will equal 3 minus 2x. To get a single y, I'm going to have to factor the y out of the left side, leaving me with x plus 1. Now the x plus 1 is connected to the y by multiply, so to get rid of it, I can divide both sides by the x plus 1. And that's going to give me that my y is going to equal 3 minus 2x all over x plus 1, which is really what my inverse is. 3 minus 2x all divided by x plus 1. Notice that your domain is going to be x cannot equal the number negative 1, so that becomes the range of the original function being y cannot equal negative 1.